All right, guys. So today, thank God for you, you have a rather short lecture. So I hope it's not going to exhaust you too much. Now, if you find any of what I'm saying difficult to follow, you have other resources, naturally. You should try to look at Calculus for Dummies, which you have available here. Good? See if that helps. Some people try to read it. Now, if you could, of course, guys, the more of you turn the cameras, the easier it is and more entertaining for me, at least, to teach you. I know, for instance, that some of you open up, log into the class, but you're not really here. That's completely obvious to me. Yeah, if you're unable, that's fine. When do you have exam? Wrong question. Do you understand the material? That's the right question. Exam will be followed, as I mentioned many times, after we finish trigonometry, so there is still time. How much time depends on how well you study. I really want you to pass it. I really want you to know the subject. I really want you to climb up, and climbing up is sometimes very steep. When is the office hours? Always after class. And you can see the syllabus is posted on my website. If you guys, this page on which I'm sitting should not be foreign to you. You should have looked into it. You should have looked into reviews, into handing assignments, into questions that you solve. When I see that few people ask me questions, I naturally assume that few people do anything. Yes, plenty of practice problems on my side. All right, so let's look at where we stopped. So we are still doing product and quotient rule, and let us review several things here, guys. Do you remember what is a stunt double in our context and what you can do with a stunt double? Do you? Anybody would like to refresh my mind? Well, stunt double is a cheaper actor that you can work more easily with a cheaper actor. You can make this cheaper actor perform the tricks that you would have liked the main function performed, right? So when you have a big movie, a big feature movie, the main actor is expensive and he's not gonna do dangerous tricks. Most actors don't want to do that. So that's what you have a stunt double for. Now, similarly here, the function with which you want to work can be a difficult function. The examples we have given, guys, is root of x, right? So f of x, for instance, equal to root of x is difficult function. It's a prima donna, I call it, right? Because, for instance, you cannot take roots of most numbers easily. You don't know how to calculate it. Polynomials are much nicer, and linear functions are even nicer. So remember, we asked for things like approximation of root of 4.01, right? What is that approximation? Naturally, you can as well say, well, it's kind of like root 4, but you can do better. You can do better. Now, what can you do better is you can see this graph. This is the graph of the function you are interested in. And this is, and you again, you're correct to say that it's kind of like root of 4. So this number is 2. And then what I can do is I can find a tangent line. And you see in here, it looks like the tangent line is not touching the 4 very well, but if I drew it better, you would see it's much, much closer, at least within a very close range around 4. So if I look here, do you see that there is very little, or supposedly very little, deviation between the black, the position on the black curve and position on the red line, right? So somewhere over here is 4.0, 0, 1. And if we zoom in close enough, exactly, Humira, the stunt double is the tangent line that you're going to see, right? So basically, what's the equation of that line? The equation of that line near 4, if I'm say using the tangent line at 4, then y of x will be equal to root of 4 in this particular case, plus the slope, which is 1 over 2 root 4. The slope always is 1 over 2 root x for the derivative. But if I zoom in at a particular x, times x minus 4. Yes, that's the equation, which is, look at it, guys, because we are taking roots of 4, it's kind of, we can easily calculate with this function. Y of x is 2 plus 1/4 x minus 4. The calculation is very clear. Look at it. I can plug any number. At no point am I required to take the root. Yes? So I am thinking that, you see, that's the black curve. Let's say here is the black curve position. That's this number here. And instead I will calculate it on the line. So I'm going to say that root 4.01 is approximately y of 4.01, which equals to 2 plus 1/4 4.01 minus 4. Are you with me? You see the benefits of it, guys. But of course, the benefits are not for approximation. You see, obviously you might ask me, well, what about root of 5? Will that help me calculate root of 5? Not really, right? Because I cannot find, the derivative will still require taking roots. Derivative is 1 over 2 root of the number where I zoom in. Yes? So this linear approximation, in your book, it's mentioned as maybe a way to estimate some numbers, but that's not what its purpose is. Okay, that's at least not in the version I'm explaining. What it is to figure out new formulas or to understand what the derivative is doing. It becomes even more important if you study complex analysis, where to imagine tangent lines or things like that will require four-dimensional thinking, which is very difficult thinking, you see. And you can understand a lot about complex functions by understanding what do they do locally. How do they function on the microscopic scale. And the derivative is just trying to describe how a function functions on a microscopic scale. I hope you understand it. What's the benefit of this stunt double process is that I can use the geometric interpretation of what a derivative is supposed to be to figure out different formulas for the derivative. Clear? I mean, we did figure out the formula for the derivative of a sum of two functions. In other words, imagine I know how to differentiate one function and how to differentiate another function. I can figure the derivative of the sum very easily by applying the definition. I could also use my idea of what the derivative is, the slope of the tangent line that I see when I zoom in on a curve. Zoom in on a curve, it starts to look like a line. And all you have to do is report the slope of that line to decide what's the derivative. You understand that, guys? You understand so you have to think formally in terms of definition, but you also want to think what the definition is trying to convey, and that allows you some flexibility, very significant flexibility that makes mathematics very simple if you follow it. Yes? So here is what I mean, guys. So suppose that I wanted to understand what's the derivative of f plus g of x. I'm just doing it for where it's not particularly important. What's the formula in terms of the derivative f prime and g prime? You understand? Suppose that I know the derivative of each function individually. What's the derivative of the sum? You already know that it's the sum of the derivatives. Yes? Now the linear approximation method just gives you another insight into what's happening. So I can say that near the point A, x equal to a, you can say that f of x is essentially the same thing as f of a plus f prime a x minus a, which I simply, so that I don't have to write x minus a, I can simply write this as f of a plus f prime a dx. Now, guys, what we're solving here is not, I don't care the answer is 4 or 7, it's not solving for a number. When you think that mathematics is solving an equation for x, you have a very wrong sense of mathematics. Okay, but the mathematics is doing is you're trying to convey a concept. So here, what I'm writing is this. I'm saying, zooming in on that curve, I have no idea what it is, but I'm saying you will see a line. And the line will have the form which has y-intercept f of a and has slope that I designate as f prime of a. Right? And the little dx, x minus a, I represent as dx. You see what this means is just that x is very close to a when I zoom in. When I zoom in, I see less and less of the x-axis about a. So I'm seeing a narrower viewpoint of the x-axis where it's close to a. That's how I know what I'm seeing is a derivative. You understand? And this reports this f prime a. F prime of a reports the derivative here, the slope of it. Clear? Now I'm supposing that I know it. So then I can take g of x. And g of x is approximately g of a plus g prime a x minus a, which I can simply write as ga plus g prime a dx. Dx is just so that I don't have to write x minus a, and to also indicate that x is very close to a. It's just a matter of just putting a sentence. You agree, guys? You can be eloquent or you can be not eloquent. And that's all it is. You're trying to be the later. If a was a number, well, you see, yeah, a is a number. A is the number at which you zoom in. Dx represents the distance between a and any other x, like the maximal distance. It says it tries to describe your horizon, so to speak, on the x-axis, your x-axis horizon. Are you all clear, guys? What that dx is? And the reason I use little d, it's a matter of analogy. It's a matter of speaking. Now here is where the stunt double feature comes in very handy, guys. You understand? Instead of adding f plus g, I'm going to add the stunt doubles. You see, because you see, if you have interaction between two actors, you simulate that interaction with the stunt doubles. You agree? So you know it from all sorts of movies, right? Where you have some sort of complicated stunts that have to be performed. The actors either incapable or not wanting to risk themselves. They are replaced by people that hopefully look like them enough to make you believe that you understand what happens to the players. Yes, it's very easy idea, correct, guys? So if I'm interested in adding f plus g, then when I say what's the derivative of f plus g, I mean take the graph of fx plus g of x and zoom in on it at the point A. Tell me what slope do you see? That's what you're talking about when you are thinking about the derivative, at least geometrically. So if I add fx plus gx, that will be very similar to just adding f of a plus g of a. You know, it's just if I add them, I can add them this way. Plus here I can see that x minus a is the same, so I will just have here f prime a plus g prime a multiplied by dx. Do you all see that? So here is your slope. So you see this tells you that f plus g will look like a line that has this y-intercept and this slope, which is the sum of the slopes of individually f and g. So that's why derivative of a sum is the sum of the derivatives viewed another way. Why wouldn't it be 2x? Because it's just simple algebra here, right? Look at it. Add this thing together. Add this thing together. One number plus another number is the sum of those numbers, and here the common thing that they can factor is dx. Do you all see that? I'm just doing algebra, basic algebra here. Just something plus something. Here it is. It's just dx is something in common that I can factor out, and I factor it out to make it look like the slope form, right? That you have the intercept slope form of a line. You understand? So from that, from doing that manipulation, I right away see what's f plus g. Now, guys, it's of course not very interesting for addition, right? You can apply the definition and it's obvious what to do with addition. Now, could you help me do the multiplication? We did it already before, but let's do it together, guys. So you tell me what to write. So now suppose the same setup. I don't need to write it, right, guys? You all see it? Same setup. Now I want you to tell me what would you do in the case when you want to figure out f of x times g of x, right? We're interested in the derivative of f times g, which means we want the slope here. Let's consider that we want the slope at a, okay? What would be the formula for the slope at a? Help me. Right, I'll be right back and you think about it. All righty then, I'm back. Is there a, what is a GC? A grade curve. I thought you mean graduate center. Yes, hopefully there is a graduate center for this class. right? Because I will make PhDs out of you. You know, guys, what it means to be Russian is that you do not stand for the price. We are ready to accept 90% casualties, 100% casualties, whatever number of casualties are necessary to ensure our victory. Study very well. There will not be curves. Right? I mean, what curve is there for either you know it or you do not know it? No curves. Right? If nobody knows it, then nobody knows it. What is f of x times g of x? So let's see what we have written there. Okay. Yes, I see it. Good, guys. So very simply, guys, look how simple is the idea. Instead of multiplying f by g, I multiply, when I zoom in, it's like I'm multiplying the linear approximation of f times the linear approximation of g. Isn't it simple? So that's the same as the product of f of a plus f prime a dx. And notice how nice when I write dx, it makes it, it saves a lot of space, prevents many mistakes, times g of a plus g prime a dx. Now, we all know how to expand parentheses. You agree, guys? I think you call it FOIL, correct? Is that what you call it in school? So we FOIL, and what we have here is, I can group it. I hope, guys, you know how to group it. I will group it by how many dx you have. Do you have no dx? Do you have dx once? Do you have dx to the power of 2? Right? So no dx, the only way to get no dx is to write fa ga. Now, how many ways to get 1 dx, which I then can factor out? So it is going to be, I can write it as f prime times ga. So it could be f prime a times g of a plus f a g prime of a dx. Do you all agree? You understand what I did, guys? I did something very, very easy. I just multiplied through and I factored out dx. So I just, you see, I have this bookkeeping. How many cases where there is no dx? How many cases where dx is to the power 1? Finally, how many cases are there where dx is to the power 2? Good, guys. And then there is one more term, and that would be where you have dx times dx. Altogether, you must have 4 terms. You see 1, 3, and there must be one more term. So that is f prime a g prime a dx squared. Moesha, are you here, by the way? All right, so guys, what is the linear approximation that I will see if I zoom in on that curve? You see, guys, what I'm doing is not really algebra or arithmetic. I'm just thinking what happens here. So dx, you understand that when I'm zooming in, dx represents the distance that I'm seeing over my screen of the x-axis from A to any point x on my screen. It's my horizon. We've seen the zooming in, right? So dx, I mean, can be smaller and smaller and smaller. It's really a limiting process. Zoom in, zoom in, zoom in, zoom in. You can zoom in as much as you like. So dx can be made less than 1,000,000. If dx is less than 1,000,000, dx squared is 1,000,000 of 1,000,000. If you understand what it means, that means that if you zoom in to the extent when dx is 1,000,000th of a meter, you cannot see it with your naked eyes. That's a micron. That's on the scale of bacteria. Many bacteria are more than 1 micron. I don't remember what's the limit of eyesight, but micron is very small. Now dx is 1,000,000th of a micron, which means if you make a micron as big as a meter, dx squared will look like a micron then. you understand what I mean, guys? And if you make dx 1/1000th of a meter, dx squared is 1/1000th of 1/1000th. Do you understand? So the smaller the dx, the less visible is dx squared, which means if you zoom in very, very close to A, there is going to be definitely a point where dx squared becomes invisible. Do you understand what I'm saying, guys? Right? There is always a point where dx squared is, no matter how, you can make it invisible, which means that the linear approximation is over here. And which means that's the slope of the tangent line if you zoom in near the point A. So that is the derivative of fx gx where x equals to A. And of course, I can just make it arbitrary x. It doesn't matter. I now have a formula for the derivative. You agree? Let's see if you can do the same thing, guys. It's a bit harder. Would you want to try figuring out the formula for the quotient rule this way? Let's try to see if you can come up with quotient rule. Quotient means f divided by g. It's the most challenging of them all. Can you do it? Let's try. What do you say? Today you seem refreshed and happy and full of life. So let's see if we can use that. Do you understand what I'm now asking, guys? I want you to use the stunt double idea to come up with a formula for the quotient, the derivative of the quotient. In terms of f prime, g prime. In other words, I'm assuming I know how to take derivative of numerator and derivative of denominator separately. But what do I do if I have quotient? Go ahead, do your best. Well, how would you even start? That's Francis is the main point. You see, you start by understanding that stunt double idea, right? It's the idea, not the process. If you understand the process, if you understand the idea, you know where to start. 2 more minutes and we'll begin together. Okay. Christina, we'll see you. Don't worry. Good. Thank you. We shall see in a moment, right, guys? We will do it together. But the point is, you know where to start. All right, let's do it together, guys. So first, we zoom in at x equal to a, right? The question is, what line do we see? And all I have to do is read the slope of that line. Very clear, yes, guys? So here, Francis, how do you begin it? So you begin by calculating f of x over g of x, yes? Now, what is that approximately? The numerator, instead of carrying the ratios, they are prima donnas. I don't want to deal with the functions. I prefer to deal with their stunt doubles. So instead of dividing f by g, I divide the stunt double of f by the stunt double of g. That's the idea. Make sense, guys? You don't deal with the functions. When you zoom in on each function individually, you see a line. Now, in terms of functional computation, it means that the line can be replacing that function, because if it looks the same, that means that the line that you see there is like the function. Its digestion is very similar to the digestion of the function. You understand what I mean by digestion? It's an input, and what it does to the input is what? It's here simply f of a plus f prime a dx. On the bottom, it is ga plus f prime, so plus g prime a dx. So all of you should be able to get to that stage. That's obvious. You understand what that means, guys? The dx part is you replace the operations of the function by linear operations. Locally, the function is to numbers very close to a. You can simulate what the function is doing by only basic addition and multiplication. You don't even need to use second power over the input, right? It's a polynomial of degree 1 can simulate it. That's a line. So what do I do next, guys? I want to see something that looks like an equation of a line. So might as well multiply by the conjugate of the denominator. Do you agree? You have this thing, I multiply by the conjugate of the denominator, and I will write it as the derivative of the bottom is not supposed to be, so it's supposed to be, well, so let's do it this way. So we have g a squared minus g prime a dx squared. You understand what I just multiplied by conjugate, and the numerator it's f a plus f prime a dx, the conjugate of the denominator. The conjugate of the denominator is ga minus g prime a dx. So far you're clear, guys? I just multiplied denominator by ga minus g prime a dx. And then I simplify what I have in the numerator. So what would that be? That would be fa plus, or fa, sorry, ga plus f prime a ga minus, you see this times that is minus f a g prime a dx. So far with me? And then there is only, and then minus f prime a g prime a dx squared. Divided by ga squared minus g prime a squared dx squared. Are you with me, guys? Do you see this formula? Now all you have to do in this formula is tell me what happens. Now it's not just algebra. Guys, what happens here? What is invisible in this formula under very high zooms? Do you see that I see all of it except where I see dx squared, right? You see, if I'm just sufficient, if I'm very, very close to the point A, and I can, even if dx I can see very well, dx squared eventually. If I zoom in very, very close to A, the closer I zoom into A, the less visible is dx squared relative to dx. Relative, you understand? Guys, you might be bothered by this idea. Of course, dx is very tiny. Can I see this very tiny thing? If it's a millionth of a micron, if dx is a millionth of a micron, you might say I don't see dx. But if you're basically zooming in to very, very close to A, relatively speaking, even if that zoom in is enlarged significantly, dx squared will be invisible. Do you understand why? Guys, if I zoom in on a millionth of a meter, so I'm 1 micron, dx squared will, if I make 1 micron look like 1 meter, dx squared will look like a micron on that scale. Are you with me? It's relative scale. Dx squared decreases, dx decreases, but if I make dx visible, even very visible, if it is under very large magnification, dx squared will not be visible. Are you with me? Can you imagine that? That's a lot of, you see, you have to understand relative scales, guys. How much bigger is a bacteria than an atom? Tremendously bigger. Okay, so considering an atom, if you study bacterial motion, you don't need to consider an atom. It's too small here. So dx squared here is not important. And you can see the formula. You see from here, guys, what's the formula? So this g prime squared dx squared is invisible. This part is invisible, and you now see what is the line. In other words, what you see is essentially this: fa ga plus f prime a g a minus f a g prime a dx divided by ga squared. You understand? If I eliminate the things that I do not see, I see this particular expression. Now, do you see where you have the line? Look at it. I can now divide it through. I divide it through, and what do I get? I have here f of a. This divided by that is f of a over g of a plus, now what's my slope? I have f prime a g a minus f a g prime a divided by g a squared dx. Here is my slope. Isn't it amazing, guys? This is my derivative of f times g, which, if I understand this idea, if I can see it, it's very, very easy, very natural. Amazing, right? That's the issue of the stunt double, guys. I see you might think, okay, in calculus 1, I can get away with it. If you study complex analysis, this becomes more and more important. When you want insight into what's happening, right? Complex analysis is very difficult to see. It's calculus, but in very in 2 dimensions to 2 dimensions. So it's graphs are very difficult to visualize, 4-dimensional graphs. They're actually 2-dimensional graphs, but in 4-dimensional space, which makes it very difficult to see. Okay, but such ideas allow you to have insights into the nature of complex functions. Wonderful. How do I know what? How do I know for this particular derivative or for complex functions? you see it mathematically. You see there's other things than sight that you can infer something from. Right? How do you go in a U-boat? Right? If you've seen the movie Das Boot, you can completely by sound or by figuring, you know, by plotting your course, figure out where you're located, but you don't see anything. You're in a tin can. Good, guys. So that's what we were doing, and I hope you understand this idea and or try to understand it. Naturally, we can also use for product rule, we can use the definition of the derivative. You see this? That's the definition of the derivative, which you can also try doing. You should be able to do it in many ways. And it's not just because, I mean, you could look this formula up in any book. The point is that if you know how to do that, you will come up with formulas that you will not find in books because there are way too many formulas. More formulas, more ideas that can be fit into any particular book, right? So you can repurpose it and make it a language that you speak. So here is, guys, now let's do, we did a few of the calculations. This is what we have established. I know how to differentiate x squared, and I know how to differentiate e to the x. The derivative of the product, it's like this, guys. I call it the traveling prime, you see? You take the derivative of the first function, multiply by second intact, plus the derivative now moves to g. You see, it travels to g. And so that's what happens here. Derivative of x squared is 2x multiplied by the second function plus, don't touch the first function, take the derivative of the second. It just happened to not change by derivatives. Clear? That's product rule for you. Now, guys, let's ask this question, guys. If you understood product rule, can you tell me, here is the formula for double, derivative of a double product. So if I have f times g, simply take f prime g plus f g prime. You see the derivative moves from one function to the next. What would be the formula and type it? Can you guess the formula if I have f g k or something like that? Take the derivative of that. What is it in terms of individual functions, f, g, and k? Type in the comments. Very good, Humira. You see it perfectly, right? So you notice the pattern very nicely. Robert, very good. Very good. Christiana, I think you just forgot prime over k, but I think you know it. Good. So some of you see this pattern, and that's very good. Why is the pattern like that? Well, you can establish it very easily once you know the pattern for pairs. Good. If you see the pattern for pairs, you can establish it. So we establish it like this, guys. So the derivative of f times g times k is like the derivative of this function in the square boxes times the second, which according to the pair-wise product rule, it's the derivative of the box function of first function times second intact plus first function intact times the derivative of the second. Now in here, I have to take the derivative of a pair of functions again, which I know f prime g plus f g prime. I know the derivative, the way it travels. And then when I simplify, I see that we have the traveling derivative. You agree? Now, let's try to consider what happens with the derivatives of higher order, guys. I will give you, maybe I'll give you one example of doing the derivative. We still know very few functions. We know only exponential functions, only e to the x, and only polynomials, and we have very, very few things available to us. You agree? Let's see, just basically, before I move on, you'll help me calculate this, guys. You see, so calculate what's the derivative of, I don't know, let's say, I really have so few options. So let's say, let's suppose we have x to the power of 1/7 multiplied by e to the x multiplied by what? I mean, there's just not a lot available. Multiplied by x squared plus 1. Right? Take the derivative of that and tell me what you obtain. Once we have trigonometry and other functions, I'll be able to give you more examples. I keep those things still in reserve. Francis, I mean, I don't see additions. That's 1/7, yes. Okay, Robert. All right, guys, let's do it together. Do you understand what's happening here? So there are here 3 functions. This function is f, this is g, and this is let's say k. Yes. So you're supposed to write something like f prime g k. That's your first term. So what is f prime? F prime, the derivative of x to the 1/7, it's 1/7 x to the power of minus. So you subtract 1 from 1/7. So that would be minus 6/7. Do you agree? Because 1/7 minus 1 is minus 6/7. Then you write e to the x squared plus 1. And then you write plus. Now the term is going to be, so this is what? This is f prime, this is g, this is k. So next you have f, g prime, k. Now that's very simple. What's f? It's just x to the 1/7. What's g prime? Ends up being e to the x. It's not interested. And k is x squared plus 1. Good. Next, plus all the same thing, except the last function is the one differentiated. So that's x to the 1/7 e to the x, and the derivative of x squared plus 1 is simply 2x. Do you see how the derivative travels? So that would be f g k prime. Good. It's e to the power of x, Giovanni. Derivative of e to the power of x is e to the power of x. E to the x does not change under derivatives. That's what we kind of established. Good? All right. So another interesting observation, guys, is how do derivatives behave under higher order. So suppose, for instance, you wanted to take the derivative of f times g once. That's f prime g plus f g prime. Now let's try to see what happens if I take the derivative of f times g twice. And watch carefully, see if you notice anything. Are you ready? So derivative of f times g twice, it's derivative of once of f prime g plus f g prime. Do you agree? And if I take the derivative here, it's product rule here plus product rule here. So applying product rule here, I get f double prime g plus f prime g prime. Applying product rule here, I get f prime g prime plus f g double prime. It's like the prime travels from here to here. The prime travels from here to here. Do you all see that? No problems there, yes? Now look what happens, guys. When I simplify, I get f double prime g plus 2 f prime g prime plus f g double prime. Does it look somewhat familiar? Does it look like something that you have been seeing before, in some other branch of mathematics, in some class long ago forgotten? No? Does it look like some other familiar formula? Similar to binomial expansion, Humira says. Geo, that's funny. Good. Binomial expansion, guys. X plus y squared. It would be x squared plus 2xy plus y squared. Do you all see that? Do you see instead of square, you have here two derivatives, right? It's like saying x squared twice f, no g. And this is y squared twice y, but no x. Very similar to quadratic. Is it true? Let's try taking another derivative. F, g, triple derivative. It's the derivative of the, it's the derivative one more time of double derivative. And when I calculate, this calculated, guys, I get this formula, which is very similar. Look at the formulas. Look at the coefficients. To the power of 1, x plus y. To the power of 2, x squared plus 2xy plus y squared. To the power of 3, look at it. Do you see the similarity? Look at the similarities. Look here and look here. Look here, look here. You see double prime on f, 1 prime on y, right? On g. Here we have 3xy squared. And here we have y cubed. So higher order derivatives are very similar, analogous to the binomial expansion. Exactly, right? So there is a much in parallel to binomial expansion here. Very useful idea. If you want to take multiple derivatives rapidly, guys, it's very useful to know binomial expansion. I will teach you perhaps how to calculate it. If you're interested in probability theory in some of the lectures, I explain why binomial expansion works, why the formula is the way it is. So to show that, guys, I introduce operators. Those are called operators, just a way to have a nice notation of what's happening here, okay? So symbolically, the derivative of f times g, it's like this is a derivative of f plus the derivative of g. So, so what do operators do? Let's say if I apply them to f times g, it's like the operator of f times f g plus derivative of just g, f times g, and that's what we get. You see? Similarly, if I square it, guys, df plus dg squared, that will be this, df squared plus 2 df dg plus dg squared. And in general, the expansion for df plus dg to the power of n can be obtained using Pascal's triangle. Okay? So what happens in mathematics, you will see, guys, that you can construct equations or operations that are over functions, right? So when you have function composition, that's the same thing as multiplication in a sense. Sometimes you call it function multiplication. So here is a way to calculate it, guys. You are hopefully aware of Pascal's triangle, but here is a review of it. So what you do is you draw 1, and then you have 1 and 1. That's expansion to the power of 1. Those are the coefficients. Then the way you obtain the next row is you have 1, and then between the two ones on the top, you write this plus that is 2, and then 1, and that's the expansion for quadratic. To obtain the cubic, you write 1, and then between 1 and 2, you write their sum, which is 3. Between 2 and 1, you write their sum, which is 3, and then you write an extra 1. Now this is expansion for the 4th power. Those are the coefficients. Are you there, guys? So you put 1, then between 1 and 3, you put their sum. Between 3 and 3, you put their sum. Between 3 and 1, you put their sum, and then you put the extra 1. So that means that the expansion of x plus y to the 4, I don't need to do any operations. I can do it very fast. It's 1 times x to the 4 plus, here you decrease the degree of x and give it to y, and put this coefficient, 4 x cubed y plus 6 x squared y squared plus 4 x y cubed plus 1 y to the power 4. Clear? If it's clear, guys, please tell me what is going to be the next expansion. If I write the next row, what do I do? Give me the next row in the comments. Type the next row in order. Okay, I see a few people notice it correctly. Yes, so what you do is you begin with 1 here. 1 plus 4 is 5. 4 plus 6 is 10. 6 plus 4 is 10. 4 plus 1 is 5, and then extra 1. That's the expansion. Very well done. Very good. And what does it mean? What does this expansion mean? It means that if I were to write the x and the y part is those are the coefficients of the expansion, right? So suppose that means that I want to expand x plus y to the power of 5. What do I write? I first write, because there is a 1, I write x to the power of 5, right? Plus, do you see this coefficient 5? I write 5, and the x drops 1 power. So it's x to the 4, y gains that power. You with me? And then the next is, what's the next term? Help me with the next term. The next term will be what? Not just 10, but 10 what? 10x cubed y squared. Do you see the power of x drops? And it's given to y squared. And the next term will be plus 10 x squared y cubed. The next term will be 5x y to the 4, and finally y to the power of 5. That's a binomial expansion. Binomial because nomial means 2 terms. Here is term 1 and here is term 2. Do you see it, guys? So that's, if you understand how to construct Pascal's triangle. I mean, I can explain to you why it works, but that involves going into combinations, okay? And it's not very hard. It's just will take us a bit away from the class. I'm very happy if you want to understand why, but right now you can also just simply see how to do it, which most of you prefer to just see how you do it, not really the explanation. Good? Not good, by the way, of course not. I mean, I cannot stand to do something I don't know. So that allows me here, guys, here is your task. Can you calculate very quickly the derivative of x to the power of 5, e to the power of x 3 times? Can you do that? X to the 5, e to the 5 3 times. Let's do it on a separate sheet. Three times. Let me help you a little bit. So this is going to be my function f. This is my function g. So first I consider to expand the derivative with respect to f plus the derivative with respect to g to the power of 3. Okay. So what that is doing, this would be the derivative of f cubed. That means take 3 derivatives plus the plus 3, the derivative of f squared, the derivative of g. In front of, is that a 2 in front of f and g? Where do you see a 2? I don't see any 2. It's just f and g, and that's the derivative cubed. I don't know. This means the symbol. That's what you think. This symbol is the derivative sign. It's a notation for take the derivative only with respect to f, right? There are different notions that come around. Plus 3, the derivative of f, the derivative of g squared, plus do you understand? I'm hoping, guys, that the symbols are not just symbols. You understand how I reason, right? So if I take derivatives, I take them consecutively, right? So that's why that idea is supposed to work. If you want, I'll re-explain it. I mean, if you understand the symbols, you understand why the analogy with products. What's being binomial expanded here, and that's the derivative operators are being binomially expanded. Now, why are they being binomially expanded? Let me just remind you in a moment. Okay, so what happens here is the next term is simply the derivative of g 3 times. Why binomial expanded, guys? Think about what happens if you take f times g and take one derivative. If you take one derivative, it's the derivative f times g plus the derivative of g times f, which if I use the notation, look at it, it's the same as take the derivative of f plus take the derivative of only g applied to fg. Do you see why that works? Applied to fg, it's just like you distribute it. It's just to create symbols here, right? You distribute it, and that gives you this result. You all see that? Guys, not because it's multiplication. That's my point in mathematics. Not because it's multiplication. Is what you do in mathematics, you notice patterns and you try to relate the patterns you notice to something you know before. So that when people say mathematics is a language, they mean that, right? Mathematics is not exactly a language, but the language part of it is that you're trying to convey the analogies or the ideas that the images that go in your mind. Now, if you take the derivative of f times g twice, that's the same as what? That's the same as applying df plus dg to what? To this expression, right? To df plus dg having been applied to fg. And then you can see that it involves expansion of df plus dg to the power of 2 fg. Same thing, expansion to the power of 2, where that means taking two derivatives. Because why the expansion works? Because of commutativity of numbers. Same thing here. That's why it works. Good. I hope you understand the idea, guys. And then let's calculate. So we don't need this. We just need this formula. Now, what is this? So I want to know what's the derivative of f. So the derivative of f 3 times. So what I have is I have f. Then I have first the derivative of f, and then f prime. Let me write it this way. The derivative of f prime is 5x to the 4. Then I need 2. The derivative, double derivative of f, which is 5 times 4, which is 20x cubed. And then I need 3. I need the derivative of f 3 times. And that would be this times 3, which is 60x squared, correct? 60x squared. So look what happens, guys. So if I want to take 3 derivatives according to this formula, that means take 3 derivatives of the first function, which means you get 60x squared multiplied by g. This means don't touch g, plus 3, the 2 derivatives of f. 2 derivatives of f is this, 3 times 20x cubed times 1 derivative of g. G is nice, it's just e to the x. You understood what I did it? This is calculating this term, plus 3 times 1 derivative of f, which is 5x to the power of 4, times 2 derivatives of g of x. Fortunately for me, g of x is just e to the x, no matter how many derivatives I take, plus this thing, 3 derivatives of g, and the function f not touched, so it will be x to the power 5 e to the power of x. And this is my third derivative of x to the 5 e to the x. You understand? So if you use this technique, of course, you can take derivatives very fast. Yes. And here is that calculation. Here we already spoke about quotient rule, right, guys? So the quotient rule is simply square the denominator. We established that. F derivative 4, sure, you just drop the power, right? So you just have to, hopefully you understand that binomial expansion procedure. Okay. This is, guys, the derivative of a quotient, which you yourself, I'm hoping, established, correct? You established the derivative of a quotient, f over g. And that ends up being the square of the denominator, copy the denominator to the top, multiply derivative of the numerator minus the roles reversed. You see, all you have to remember, it's very important to do it in order. Square the bottom, copy the bottom, take the derivative, and then minus. It's not a product rule on the top. It matters what you put first, you see? So denominator squared, denominator, numerator, derivative, minus, and then role reversed. Please calculate the derivative of x to the 5 divided by 2 times e to the x. Justin, you forget that the derivative of a quotient is not quotient of derivatives. Obviously cannot be right, Justin. Guys, look at this formula. It's right on top of this expression. Okay, Joseph, good. So let's do it together, guys. It's very simple. Of course, you can try to memorize this formula, but it's easy. Things are easy to forget. Okay, let's do it together. So what do you do, guys? You take the derivative of the, so first you take the denominator, you square it. Here it is squared, and then you copy the denominator and multiply by the derivative of x to the 5, minus the roles reversed. Now, when you square it, it's 4e to the 2x. What do you get here? 2e to the 2 times e to the x times 5x to the 4 minus the derivative of the bottom multiplied by the top function without touching it. Good. Now calculate the derivative of 1 over x to the power of 5. Very good. And you can see that, guys, by applying the quotient rule, for instance. Yes. So we have what? We have the denominator squared, copy the denominator, derivative of 1 minus derivative of numerator times 1. Derivative of 1 simply is 0, so we're just left with derivative of the numerator, so the derivative of denominator with a minus divided by this number squared. So what happens? It simplifies to minus 5x to the minus 6, which has been expected. Good. So there is a few more examples here, but let's stop for today. And I'll see you on Thursday. All right, guys.